Hello, everyone. Welcome back to perhaps the next part of our walkthrough of AP Calculus AB by Richard Song. Moreover, let's talk about how the direct substitution property doesn't work immediately sometimes. And that starts off with the things called indeterminate forms. When I say indeterminate form, I mean a case where if we were to plug in the value of x that the limit is approaching towards, our final result gets us something that looks like 0 over 0. Keep in mind, though, that although it says 0 over 0, we're working with limits. So this pretty much means something very close to 0. So 0 point, let's say 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, onwards to 0, 0, 0, 0, 0, 1 over another small value. Now, the issue with that, however, is that there are some properties about 0 over 0 that doesn't lead us to anywhere. For example, is 0 over 0 the same values? Do they cancel out to become 1? Does the 0 over 0 become 0 because it's 0 divided by a different number? Or does 0 over 0 become undefined because anything divided by 0 is undefined? Well, because again, we're not working with exact values of 0, all we can do is assume. But we don't want that. We want definitive answers that we can determine an answer with, hence the term indeterminate forms. And so going forward in AP Calculus, AB and BC contain several different types of indeterminate forms. One that we'll be talking about today and in the next video is going to be using anything that gives us 0 over 0. Other examples, however, include something that looks like infinity over infinity, or maybe even infinity minus infinity, or maybe even 0 times infinity. Hey, how about infinity to the power of 0? And maybe 0 to the power of 0. We will come across all of these things at some point in our mathematical careers here. However, I will give you a sense of relief in that we will only be focusing on the first four within the scope of AB. The latter two, however, will be things that are going to be covered in BC. So you don't have to worry about that for another year. Now, much like 0 over 0, infinity over infinity suffers the same identity crisis where do the infinities cancel out? Is one infinity larger than the other? And that same argument can be said about the infinity minus infinity part. Is the positive infinity larger than the negative infinity? Or 0 times infinity? Does the 0 overpower the infinity, or does the infinity overpower the 0? All of these things, again, can be answered, but the only way we go about answering questions that give us any of these indeterminate forms is by a certain set of approaches. In the case of 0 over 0, specifically those that involve a rational expression, most times all we have to do is factor the numerator and denominator and cancel the common factor. Hey, those are the two steps they want you to do. Now the example follows the same route, where let's say we're given limit as x approaches 3 of x squared minus 9 over x cubed minus 27. If I were to plug in 3 directly into all the values of x, I'll get, 3 squared minus 9 over 3 cubed minus 27, which 9 minus 9 over 27 minus 27? That's looking like 0 over 0. That won't do. So what we've decided to do is consider the fact that the rational expression can be simplified as follows, where the numerator becomes, well, due to difference of squares, x plus 3 times x minus 3. But what about the denominator? Fortunately for us, when we're dealing with an expression that looks like the sum or differences of cubed values, they give you a formula sheet. And in this case, we're going to use the second case. And that makes our job quite easy. Turning it into x minus 3 times x squared plus 3x plus 9. I'll recognize that the x minus 3's cancel out. I say, oh, okay, well, that means the limit as x approaches 3 of x plus 3 over x squared plus 3x plus 9 is an equivalent expression, and maybe, because I can't factor it any further, maybe there might be a chance that I do not get a 0 over 0 answer. And so we plug it in, and we get that 3 plus 3 over 3 squared plus 3 times 3, 9 plus 9, which becomes 6 over 9 plus 9 plus 9, which becomes 6 over 27, which is 2 over 9. Now keep in mind, one of the things that I am very, very strict about is the fact that I am always writing this notation in front of the rational expression until I am performing the direct substitution property. Any other steps before doing so requires this in front. We want to develop good habits. And so remember, limit notations should always be written until you fully commit to directly substituting your x values. Let's try a couple questions and see if we fully get it, starting with evaluate the following limits of exercise 7, number 1. Now, like I said, if we plug it in directly, I get that this is going to be negative 2 cubed plus 8 over negative 2 plus 2. Negative 2 cubed becomes negative 8 plus 8 over negative 2 plus 2, which is very much an indeterminate form that looks like 0 over 0. And so my brain should immediately say, hey, okay, maybe there's something that could be factored out, especially since it's a rational expression. And thankfully, we have a formula cheat sheet about factoring two sums of cubed values. And in this case, it's the numerator. And so the numerator becomes limit as x approaches negative 2, don't forget that part, of x plus 2 times x squared minus 2x plus 4. That is all over x plus 2. Thankfully for us, x plus 2 exists in both the numerator and the denominator. So limit as x approaches negative 2. Again, I haven't substituted negative 2 in yet, so I'm going to keep writing this, of x squared minus 2x plus 4 over 1, which just becomes x squared minus 2x plus 4. And now I say, hey, maybe it's time I plug it in and say negative 2 squared minus 2 times negative 2 plus 4 becomes 4 plus 4 plus 4, which therefore is a clean number of 12. Again, very different from the 0 over 0 indeterminate form I initially had. Now on to a peculiar type of question, such as question number 9 here. Just using context here of what exercise we're still in, if I were to plug in 2 to both the numerator and the denominator's x values, I get that it's going to be 8 minus 8 minus 8 plus 8 over 8 minus 8, which, you guessed it, is going to be 0 over 0. I need to factor this. The issue is, unfortunately, the numerator looks a bit more trickier to factor, but we're going to use what we called the factor theorem, where if a value of x turns a polynomial into 0, that is indeed a factor. So if x equals a turns x cubed minus 2x squared minus 4x plus 8 into 0, then x minus a is a factor. And in this case, x minus a is going to be x minus 2. But how does that factor the polynomial in the numerator here? Thankfully, we're going to use what's called a synthetic division process. Don't you remember it? Well, let's go through the motions, see if it can refresh your memories. Starting with the 2 on the leftmost side, then I'm going to write down all the coefficients of the polynomial that we're dividing by x minus 2. In this case, it's going to be 1, negative 2, negative 4, and 8. First step, the 1 just drops down, and 2 times 1 is going to be equal to 2. Add those up, it becomes 0, times 2 again becomes 0. 0 plus negative 4 becomes negative 4. And last but not least, 2 times negative 4 equals negative 8. And add those up, and phew, I get a remainder of 0. X cubed minus 2x squared minus 4x plus 8 can be factored into x minus 2 times x squared plus 0x minus 4, aka x minus 2 times x squared minus 4. Now let's apply that to what we have so far, in which that limit as x approaches 2 of the new numerator x minus 2 times x squared minus 4 over x cubed minus 2x squared. Let's see if there are other things that could be factored further, starting with the fact that x squared minus 4 in our numerator can be factored further. And so limit as x approaches 2, and remember, I have not substituted 2 yet, so I'm still writing the limit notation, of x minus 2 times difference of squares, x plus 2 times x minus 2 over, we can factor an x squared from both terms in the denominator, so x squared times x minus 2, and look at that. I can factor 1 x minus 2 from the numerator with the 1 in the denominator, and everything else stays as is. And so to repeat, limit as x approaches 2 of x plus 2 times x minus 2 over x squared is what we get so far. And let's see if plugging it in this time gives us a different ending, where 2 plus 2 times 2 minus 2 is my numerator over a 2 squared. And the numerator is going to be 4 times 0 over 4, which is going to be 0 over 4, which, not undefined, is not indeterminate because it's not 0 over 0. Rather, 0 over 4, using basic understanding of math by now, is going to just be 0, which is a valid answer I can conclude with. Okay? And so, yeah, maybe it's not the ending that you hoped for, but this is a good lesson in that 0 is a valid answer I can conclude with. It is not an indeterminate form, and so this is not something we need to work beyond. I can close off this question, say the limit is approaching 0, and end my day with a smile.